Hey physics fans, today we're going to be talking about conservation of angular momentum, which is in chapter 11.3 in the text. Now, in order for conservation of angular momentum to occur, we need two conditions to happen. The first of those conditions is that we have a closed system. A closed system meaning the mass in the system does not change over time. The second of those conditions is we need an isolated system, which means the sum of all external forces on the system is equal to zero. And if all the external forces that are acting on the system is equal to zero, there's also no external torques acting on the system, which means that the angular momentum does not change over time. And then you can state the law for conservation of angular momentum, which is that the initial angular momentum is equal to the final angular momentum of a system of particles. So you have to sum the system. Now this is easier to show in a problem, so I'm going to go ahead and grab text problem 11-58 alpha, and I'll be right back. Oh, here's that text problem. Okay, so here we are at text problem 11-58 alpha for conservation of angular momentum. Now after reading the problem, you notice that there's a collision and there's some kind of rotation going on between a point particle and a disk. Therefore, it's a conservation of angular momentum problem with a collision. Our task in the problem is to calculate the final angular velocity of the rotating system after the collision. Because it's a conservation of angular momentum problem, the physics that we use is our law for conservation of angular momentum. And we notice that it's colliding with a disk, so we need the inertia for a disk, which is on the back of your physics reference card. Drawing the problem, it's in 11-58, and in conservation of angular momentum problems, we like to draw it during the solve step. So we'll get to that in just a second. The given variables are the initial velocity, the radius of our disk, and then the mass of our point particle, shown as a lowercase m, and our disk, shown as an uppercase m. We're assuming that it's a closed and isolated system because those are the conditions that we need for conservation of angular momentum. So let's get over to the solve step. Now, just before the collision, we have a point particle that's traveling with some velocity through space, and a disk that's not moving. After the collision, we have a point particle that's attached to a disk, and they're both rotating through space. So we have our just before picture with the mass and velocity of our point particle giving us a linear momentum, and a just after picture showing a rotating system with a linked coordinate axis. Summing up the initial angular momentums in our system, the only thing that's moving is our point particle. So we have to take the cross product between the position vector, which is going to be the vector from our axis of rotation to where it's going to collide with the disk, and we take the cross product between that and the linear momentum, which is the mass times the velocity of our point particle. Now, because we're taking the cross product, we have to translate that momentum vector so that we can look at the angle between the position vector and the velocity vector. Now, looking at the just after picture, we have an entire system that's rotating at the same final velocity. So we have to look at the inertia of the entire system times the final angular velocity. Now let's start substituting things in. Taking the cross product between the position vector and the momentum vector, we get the position vector, which is the magnitude of it is the radius of the circle, times the mass, times the magnitude of the velocity of our point particle, times the sine of the angle between them. And we set that equal to the inertia of the system, which takes into account the inertia of the disk, which is 1/2 times the mass of the disk, times the radius of the disk squared, plus the mass times the radius of the point particle, which is sitting at the edge of the disk, also squared. Remember, this is the inertia for a point particle. And we multiply that whole quantity times the final angular velocity of the system. Rearranging that equation, we can solve for the final angular velocity of the system as an algebraic expression in terms of all of our given variables. Once again, remember, when you're solving for algebraic expressions, it has to be what your task is in terms of all of your given variables. Substituting the values for our variables in and evaluating, we get 7.40 radians per second. Now, the least number of significant figures in the problem is 1, so we report it as 7 radians per second. Additionally, it's asking us to solve for the final angular velocity, so we can look at the final angular velocity, and since it's rotating around, we wrap our fingers in the direction of rotation, and the direction is coming out towards me. Now, checking, it's an angular velocity, so our units are radians per second. Our significant figures, as we discussed, is 1, and it seems like a reasonable answer. Thanks, physics fans, and we'll see you next time.